Hello and welcome back to another Jet2 Guide video. So today we are looking at a new topic for the channel, which is meteorology, and I'll kind of see how many views it gets. If it's getting popular, I'll keep doing it. If people are not interested, I'll just scrap the whole thing. But this has been an interest from mine for about 3 years, so I decided to give it a go. Particularly, I'm interested in cold weather and long range stuff, so not the nitty gritty exact temperature forecast, etc., or what it's going to be doing tomorrow. I'm more interested in what it's going to be doing months in advance, particularly in winter. So this video is going to be looking at jet streams, their associated vortexes, and the effects on UK weather. So this is a summary of what polar vortexes are, and essentially a sentence. The polar vortexes are two vortices that spin in a westerly-easterly direction in the northern hemisphere. Now, as I said before, there's two of them. So the first one is the stratospheric polar vortex, and it's located in the stratosphere, and it's between a height of 23,000 and 200,000 feet. So that's going all the way up from the stratosphere into the mesosphere, and it's formed because of the temperature contrast between the poles and the mid-latitudes. It is usually strongest in December, due to the stratosphere being coldest in December. Thus the most zonal weather for the UK at least occurs in December. You'll see why later on when I explain atmospheric coupling. And the boundary of the stratospheric polar vortex, which I'll refer to as the SPV, is the stratospheric polar jet stream, which is more commonly known as the polar night jet. And it's known as that because the stratospheric polar vortex only really forms during the polar night. So in winter, when very little sunlight reaches the North Pole, because if you imagine the Earth, this is exaggerated of course, it's on a tilt in winter away from the sun. The northern hemisphere is tilted away, so very little sunlight reaches this region up here. So that's why it's called the polar night jet, whereas the tropospheric polar vortex exists all year round. So the summary of the tropospheric polar vortex is it's located in the troposphere and between a height of 30 to 39,000 feet. It's formed because of the pressure gradient between the rising air colliding at subpolar low. It's strongest in December due to atmospheric coupling, which I'll explain later on. And the boundary of the tropospheric polar vortex is a tropospheric polar jet stream, which is just more commonly known as a jet stream. Everyone pretty much in the UK has heard of the jet stream. You hear about it being talked about constantly on the Weather Channel, and you probably know if the jet streams to our north, on the warm side; if the jet streams to our south, we're on the cold side. That's probably the most you know about it, and you know that if it's across us, it brings wet weather. And as you know, the jet stream acts as a kind of driver for weather. So the tropospheric polar jet stream also acts as a continuous, it's mostly continuous, it can break up in the summer cold front, which another name for the tropospheric then polar jet stream is the polar cold front. Because what you get if you picture Earth here and you have the jet stream moving across, to the north of this you've got cold weather, to the warm of this, south of this you've got hot weather. So it could be a warm front here, it's pushing up as a warm front. If it's moving northwards, you got the polar warm front, or we've got the polar cold front here, and it's driving cold air southwards. So that's why it's also called the polar front. It's got lots of different names. Lots of things in weather will try and confuse you because it's got lots of different names, but if you know them, everything starts to make sense essentially. And this diagram up here actually is showing the stratospheric polar vortex, its potential velocity. So as you can see on the outside, it's around 25 PV units. On the inside, it's at around 30 to even 40 right in the core there. Starting to get into those light pinks right in the centre. But that's just showing how strong it is, essentially. And this also shows the temperature. So you can see it's quite cold, and the ozone we don't really need to worry about for now. So, stratospheric polar vortex. The stratospheric polar vortex only exists from August to April, as the temperature contrast is enough to create a high altitude, low pressure system. Low pressure vortex, same thing essentially. And it is formed because of the strong temperature contrast in the stratosphere between the mid-latitudes and the poles, beginning in late summer. I think the average date is around 24th to 25th of August. And when the temperature contrast is greatest in December, where the poles top out around minus 71 degrees, the winds are typically the strongest, because the temperature gradient is greatest, the strength of the winds is strongest. That's the fact with most vortexes in the northern and southern hemisphere. And these strong winds can propagate down into the tropospheric polar vortex, leading to a very strong jet stream, and putting the UK into a zonal flow. By zonal, on a synoptic chart, there will be very flat, strong westerly winds and inflated NAO, North Atlantic Oscillation. I'm not going to be going into the NAO this time. Next time, again, if there is a next time, I'll go into it. But for now, I'm just sticking with the AO, which I'll explain a bit later. While we're in this very cold state of the stratospheric polar vortex, we're getting strong westerly winds. The Arctic is actually will be freezing, like really, really cold, like minus 50, like usually around minus 30 up there, minus 40, but it can get down to minus 50, 60 in very strong polar vortex times. And the SPV is why winter is wet and windy, and why summer is normally warm and dry. Because when it collapses in April, it literally only takes a couple of weeks for effects to be felt in the troposphere, and then the jet stream weakens significantly. So in winter, it kind of acts as a driver for the jet stream, and it's forcing it along, it's chugging it along. That's why we get wet and windy. And in summer, when it's not there, the jet stream is kind of weak and all over the place, and other things drive the jet stream to make it stronger, essentially. So sometimes the stratospheric polar vortex can collapse in winter due to events called sudden stratospheric warmings. Simply, these cause an increased temperature in the stratosphere. It's around plus 70 or 80 degrees usually, within a matter of days. So it's a very violent event in the atmosphere. And so this kills the temperature contrast, leading to the collapse of the vortex. And if there's no vortex, there's no westerly winds to lock in the jet stream. Thus, if one of these happened in winter, usually Arctic air spills southwards. And this can either be into America, China, the UK. It's kind of random, but I think the percentage is roughly 66% chance that we get some sort of cold spell if we have an SSW, but it's not always guaranteed. And these three diagrams, so I'll explain the top left one. This is showing the average temperature at 10 HPA, so that's right at the top of the stratosphere here. And as you see in December, when it's coldest, if I had another chart here comparing the winds, you would see there's a direct correlation, essentially. So you get strongest zonal flow at the coldest point, and you get weakest zonal flow at the hottest point. Now you actually get reverse zonal flow, so the winds travel from west to east. I think that's something to do with the Coriolis effect. I'm not entirely sure, but I know if we look at these diagrams, so at 60 to 90 degrees here, it's labelled stratospheric polar vortex. In January, it's very strong. It's very much there, very much westerly winds. However, you can see in July we're going to get weak easterlies. But you can see down here, the tropospheric polar vortex is existing all year round, but it is weaker in summer, as you can see. And remember, in the southern hemisphere, the Earth's tilt is tilted away, so southern hemisphere gets the southern stratospheric polar vortex, and it kind of switches around like that. So it's constantly oscillating between the southern and northern hemisphere, and they form every year. They're very normal in the weather, and this diagram up here just shows the stratospheric polar vortex and the tropospheric polar vortex, like there. So this is a tropospheric polar vortex, and it exists all year round, and it's caused by the pressure gradient between the feral and polar cells. This boundary of the vortex is the tropospheric polar jet stream. This jet stream directly affects the UK's weather systems, unlike the polar night jet. So I'm talking about stratospheric polar vortex, that has secondary effects. Now, like the SPV, it is weaker in summer due to the pressure gradient being weaker, due to the temperature gradient being less. Unlike the polar night jet, the jet stream moves north in summer and south in winter. That's why in summer it's generally more warm and pleasant, and in winter it's generally wet and cooler. And doesn't, by south I don't actually mean it moves south of the UK. I mean it's usually sat directly across it, causing regular depressions to move in and cool temperatures. For somewhere like southern Sweden or Finland, that slight difference massively allows the temperature to drop, because it's completely clear of the jet stream. It's actually on the cold side. We're normally in between, we're literally in between them, so Scotland can actually get, it's actually significantly colder than southern England. And if you've never been up there for a prolonged period of time in the winter, you think it's the same, but it's definitely about 5 or 6 degrees colder, I reckon, than the heart of London in winter. So where was I? Here we go. And the jet stream can meander about. So imagine it like a rubber band. The more tension you got, the more circular it is, right? When you apply tension to a rubber band, you're pulling outwards and you've got more tension. If it's loose, it's kind of all floppy like this. That's kind of similar to jet stream. When there's no tension, there's no energy, when there's no like driver kicking it into a strong state, it's going to be weak, it's going to meander about, and these meanders are called Rossby waves. Now, if these Rossby waves, they're often called planetary waves, are poleward propagating, they can disrupt the polar night jet, leading to the previously mentioned SSW. The larger in amplitude these waves are, the greater disruption to the westerly flow is caused. A weaker TPV means a more wavy jet stream. Weakness can also be caused by a higher than average pressure in the Arctic region. So I'm not going to go into depth about SSWs and that sentence in particular until another time, but essentially what you get is you got the tropopause, and a tropopause is the boundary between the troposphere and the stratosphere, and that moves lower in altitude the further north in latitude you get. So at 90 degrees it's very low, it's at like 23,000, while at 0 degrees it's around 55,000 feet. Now at 60 degrees, let's say you have the jet stream, it's moving straight across. So imagine this is a cross section and it's moving off into the distance. Now if this jet stream meanders, so there's a big amplitude in it, if it goes up here, it can infiltrate into the polar night jet. You kind of see what I mean, because it's at a lower altitude, it's more easy to get into the stratosphere and disrupt it. And essentially, if you have something coming around in this direction and you have a large Rossby wave coming at it, disruption is going to go bang, it's like a wave, it's going to break. And that's going to cause all sorts of issues. So again, I'm not going to go into depth about it, but that's roughly what happens. And as I said earlier, weakness can also be caused by higher than average pressure in the Arctic region. So if you have higher than average pressure, what you're going to get is less pressure gradient for the tropospheric polar vortex, thus lighter winds. This links into the AO. Now the AO, Arctic Oscillation, is a reflection of the state of the atmosphere in the Arctic region. This is a part of the northern annular mode, and there are two phases to the AO, one being the negative phase and the other being the positive phase. During the negative phase, pressure is going to be higher than average. That means the stratospheric polar vortex is going to have weaker westerly winds, and if atmospheric coupling is in place, the tropospheric polar jet stream will be weaker as well. If this jet is weaker, it can lead to meanders in the jet, which can drag colder Arctic air infiltrating into the UK. And the diagram on the right shows these two states. So this is a little diagram here which shows basically the stable polar vortex. So with a positive AO, with higher than average pressure, with lower than average pressure, you're going to get really deep low here. It's going to have really strong winds, and that's going to reinforce that strong jet stream. With a negative AO, you've got higher than average pressure. That means less pressure gradient, less temperature gradient thus, and you get more a weak, wavy jet stream. Now, generally I've found a strong correlation between the AO and the temperature in the UK. I find it very reliable as a forecast to see whether the UK will enter a colder or warmer than average air mass. A lot of the time the Rossby waves align to put the UK on the cold side of the jet. Now, I'm not going to go too much into depth about how that works. One, because I'm not that confident on it, and two, because it's very, very complicated. But what I mean by that is, let's say you have a positive AO, and so that's going to lead to generally a straightened jet stream. So for the UK here, that straightened jet stream is generally going to be to the north in summer, and in winter it's generally going to be across it. So there's very reliable you're going to get cool and wet weather with the positive AO. Now, in winter, what I find is these Rossby waves perfectly align themselves to give colder weather usually. So for the UK here, these Rossby waves dipping up, dipping down, dipping up again, we generally are on the cold side with a negative AO, which is good because we get snow. And I don't know, yeah, I can't fully explain it, but it's something to do with a high pressure system setting up here, and you can get something called warm air advection, which is WWA. Sorry, warm air advection, WAA, which kind of builds the high end. Now, that's all a bit over my head, but I know that's roughly what happens. This chart down here is what we call an AO index. So it's by, I think it's by NOAA. And what it does is it gives a forecast of the AO. So when it's up here, we have a positive AO, so we know there's lower than average pressure. When we hit down here, we have a negative AO, so it's higher than average pressure. So what if you've been in the UK right now, you know it's quite cold. It's gone feeling quite autumnal, and that's because the AO is negative. And it's forecast to go slightly positive next week, and guess what's going to be forecast? Around 15 to 16, even higher temperature, around 20 degrees actually. They go into the warmer phase, but then it quickly kind of forecasts to drop back down. So what I'm expecting as we go into mid-September is, as we hold around this neutral phase, we might get a stormy period, and then it might be quite cool. So I'm actually going to do an October forecast around late September, if I get my stuff together. And I want to see how strong this correlation is, because I've watched it for about a year and a half now, and generally it's pretty bloody accurate. But there's lots of other drivers as well, which I'll look at. But there you go. There is, I think that's it now. So I've just got black pens here if I want to draw anything out. But yeah, so that is it. Thanks for watching, and I hope you enjoyed, hope you learned something, and I'll see you in the next one. Goodbye.